Brice joined Airbus Helicopters in 2003 as a dynamics and vibration engineer in the general engineering department of the design office. After 12 years of experience on different military and civil aircraft, including in Germany and South Korea, he became Innovation Project Manager in the Research and Technology Department, where he was involved in several innovative systems like landing gears, rescue hoists, electromechanical actuators, and retractable horizontal stabilizers, before becoming Chief Engineer of the RAeS demonstrator in 2016. As Chief Engineer of Racer, Brice is driving the development of this innovative compound helicopter funded by the European Clean Sky 2 programme, which involves 40 partners in 13 countries. After a very successful first flight in April 2024, the prototype has realised 8 flight hours and opened a very large part of its flight domain. Brice is now preparing the next phase of the Racer flight campaign, which includes mission demonstration and hybrid eco-mode functions, of which we'll be hearing more tonight. After the lecture, there will be some time for Q&A from both here in the room and from online. And for those of you joining online, please do post your questions in the chat and we will try and get through as many as we can. And for those of you here in Hamilton Place this evening after the Q&A, there'll also be a drinks reception in the Marshall of Cambridge room, kindly sponsored by Airbus. So, without further ado, I'd like to hand over to Brice. The floor is yours.
Thank you very much for this introduction, and I'm really pleased and honored to be here tonight in London in the Royal Aeronautical Society. It's a privilege for me to present you the Racer. The Racer demonstrator is an aircraft compound aiming to fly fast while taking off vertically. It fills the gap between helicopters and fixed wing. Innovation is in the DNA of Airbus Helicopters. And the Racer demonstrator is a very good example of how we make our purpose concrete. We lead helicopters and pioneer new VTOL for a sustainable future. This demonstrator is very innovative. More than 90 patents have been filed during its development. So let's watch a video presenting some of the main features and innovation that are embarked in the demonstrator. Great. Funded by the European Commission within the Clean Sky 2 program, it has involved 40 partners in 13 countries. And it was possible due to the high level of collaboration among all the partners. Universities, small SMEs from automotive, institutes, aeronautical companies. And it was key for the success because we could extract all the best of each partners that participated to the project. I'm really happy here to be in the UK and to highlight that UK has had a key contribution to the project. I want to warmly thank the Astral Consortium formed by Airnova, Humble Aerostructure Company and the University of Nottingham that were responsible of the design and manufacturing of the wings, which are a key element of the formula. Now, what are the main objectives of this project? We want to demonstrate that we can fly 50% faster than a conventional aircraft. We want to demonstrate that we can cover twice the surface than a conventional helicopter can cover in 1 hour. And while doing that, we save some emissions, both in terms of fuel consumption and on noise footprint. On top of that, we want to demonstrate the affordability of the formula, because the best innovation is the innovation that is able to meet the market needs. What are the missions where speed matters? There are many missions in the civil world, like search and rescue, emergency medical and services, intercity shuttle, police missions, where the speed will bring added value to the citizen and the potential customers we have in front of us. So now let's go a little bit more into the technical fields, how the Racer formula works and flies. What we have to consider is that the limiting factor for the conventional helicopters is the speed at the main tip of the main rotor blade, at the tip of the main rotor blade. When you add the rotational speed and the advancing speed of the aircraft, you are close to Mach 1, and it's something that is not viable for a safe flight, and this is our limit. So the first thing you have to do when you want to fly faster is to decrease the rotational speed of the main rotor. When you decrease the rotational speed of the main rotor, you have less lift. And that's why we have the wings, because as we have less lift, we need to compensate. And then the second parameter that is key for the high speed is the drag. We need to reduce the drag at the minimum, otherwise the formula will not be competitive in terms of power needs, efficiency, speed that we can reach. For that, we want to keep the rotor as flat as it can be, with not a lot of collective pitch, not a lot of cyclic pitch, and if possible, zero. So that the rotor at the end is very flat and acts like a wing. And we don't use the main rotor to provide the propulsion force to reach the speed. And therefore, we need the lateral rotors. The lateral rotors, they are providing the propulsion force in order to move the aircraft forward. And as we have the lateral rotors, we thought that it was a good idea to use them to do the anti-torque function. That's why we don't have a tail rotor. Okay? So, very simple formula. One main rotor, two wings, two lateral propellers, and that's it. So, at Airbus Helicopters, we have a long and strong history of building demonstrators, exploring new concepts, learn from them and apply it to the market. In that case, you can see in this slide that we have the picture of the X-Cube that we flew some 10 years ago. And at that time, it was to answer to the question, is this formula viable? Can we fly fast with this formula? And the answer was yes, it works. And then we learned from the X-Cube, the experience, the measurement, the tools for simulation. We learned from that, and we created the Racer that is, in that case, a fully operational aircraft that is able today to demonstrate some missions. So it's very close to something that can be used by potential customers. I spoke about the drag, and I want to illustrate a bit the efforts we did in order to reduce the drag. A little bit later during this presentation, I will give you some numbers, but first of all, I will describe the theory that we had. In red, you have the lines that represents what should have been the X-Cube if we would have done it at the same weight of the Racer. So you have seen that between the X-Cube and the Racer, we did a lot of efforts, mainly on the fuselage, to limit the width at the minimum without jeopardizing the comfort. In parallel, we worked a lot on the main rotor with a full fairing of the main rotor so that we limit the drag at the very minimum, and you can see that theoretically we should be able to save 25% of the drag of the main rotor. And in total, in theory, we have a reduction of 45% of the drag when we compare to the helicopters that is in the same range in terms of mass. I told you the wings are a key element of this formula, and it is true. And I will explain you why. There are some reasons why between the X-Cube and the Racer we decided to implement these box wings. The first is that we decided to put the lateral rotors in pusher position and to implement the box wing so that it protects the people that want to embark or disembark in the cabin. In fact, we created a safety area that you can see here where the blue arrow is, so that the people are in total security when they embark and disembark in the aircraft. There is approximately 7 meters to walk when you disembark to be close to the lateral rotor blade. And it's protected by the box wing. The second reason to implement the box wing is the fact that when we have only one wing, we penalize the formula because seen by the rotor, the surface of the wing is quite big, and the downwash effect is detrimental for the hover phase. When we are able to superimpose the two wings, we limit the surface seen by the main rotor, and we improve the performance in hover. The third reason is what is described here, on the right top corner. In fact, when the wind is coming through the wing, it creates a vortex. It's the blue line that you see. And we have made the architecture so that the lateral rotors are turning in the opposite way than the vortex created. It means that, seen by the blades, there are more speed than just the rotational speed. And it is an increase of 10% of performance that we expect from the theory and that we have measured and confirmed. And the last reason, it is not on the slide, but I will describe also. Later on, you will see that in the upper wing, there is a shaft which is linking the main gearbox to the lateral gearbox. It's a 3-meter long shaft. And this shaft has some constraints in terms of misalignment. So it means that there is a requirement for the wings that on the full flight envelope, you must respect a displacement of not more than 14 millimeters. Otherwise, you start to damage this shaft. And when we have a box wing, which form a kind of torsion box, you are much stiffer than what you can have with only one wing. So, box wings is a key element of the formula. We have also an asymmetric tail boom, patented one, as well as the box wing, on this demonstrator. And this asymmetric tail boom is here to improve the performance in hover. When the downwash of the rotor is blowing the air through the profile that we have defined, that you see here, it creates a force in the lateral direction that helps the lateral rotors to provide the anti-torque function. And it's about 10% that we expect to have. And here again, it is something we have already checked during the 8 hours of flights we have performed. It works. By the way, it is something, it is one technological brick we can use on conventional legacy fleet, because it will also improve the hover performance of the conventional helicopters. On the left side, you have also the flaps that are mentioned. On both the upper wings and the lower wings and the vertical fin, we have some flaps that are actuated with electromechanical actuators that are secondary flight controls that we are using to fine-tune the equilibrium of the aircraft during all the flight phases that we want to optimize. I will come back a little bit later on this topic when I will speak about noise reduction. Now, simplicity and communality. You have a picture which is describing how the mechanical system is done on this aircraft. Everything is linked together. Everything is turning at the same rotational speed. There is no complex mechanism. It's all technology that we are mastering, TRL9 technology. And on top of that, all the upper deck, engines, main gearbox, rotor mast, rotor blades are fully compatible with a conventional aircraft. You can take it and put it on a conventional, it works. In the specification of the main gearbox that we have developed, co-developed with our partner GE Avio in Italy, we have put the requirement that it shall be compatible with a conventional aircraft. it means that we have the capacity to implement a rear output so that we could transmit the torque to a tail rotor if we want to use it on conventional aircraft. And then you have to come back a little bit to the affordability that I mentioned in the beginning of the presentation. We believe that if we are able to provide solutions that can be used both in conventional architecture and in high-speed architecture, at the end, for potential users, customers, whatever it is, in civil or military, it will be an advantage, because all the system that I described here represents the main part of the cost of a helicopter, both for the RAeS, but also for the operational costs. In terms of maintenance, notably, this is something which is really at the heart of the cost of the aircraft. So at the end, we want to make it simple and to be able to reuse the maximum of parts that we have on different formulas. Something which is very important that I did not mention too much in all the previous presentation I made by the past is the longitudinal center of gravity of this formula. This formula is perfectly centered in terms of longitudinal center of gravity, and it is a key point for the aeronautics today. It means that this formula is stable without any additional help. We don't need the autopilot to pilot this formula because it's perfectly centered. And then there is a lot of implication of that. We have a robustness of the development. We have also the fact that to manage the failure of the systems that are involved in the autopilot, for example, it's much easier because in case of failure, it is not catastrophic. And why we are able to obtain this center of gravity? So I need to mention that between the preliminary design review that took place in 2018 and the first weighing of the aircraft in 2024, 6 years, we didn't degrade the center of gravity location by any millimeters. And it's not because we are good. It's not because we are better than the others. You just have to look at the picture and you will realize that the red dot line is the axis of the main rotor, and all the heavy masses, the heavy systems, are aligned with this red dot line. You have the lateral rotors, the lateral gearbox, the wings, the main gearbox, the engines, the rotor, the blades. So whatever we do during the development, if we are very bad, if we are not skilled, we will not degrade the center of gravity. And this is something which is really key for that kind of formula where you need to go fast and to ensure the stability of the aircraft. What did we do during the first flight test campaign? So we did 8 hours of flight, as you mentioned in the introduction. We made the first ground run on the 6th of April 2024, and the first flight on the 25th of April 2024. We flew up to 80 knots before stopping the flight because we have a small chip in the chip detector of the main gearbox. It's something which is quite usual when we do the first flight. Everything is not fully clean, and sometimes we have this kind of events. What was really interesting is the discussion between the pilot and the flight test engineer during this flight. And you can imagine that the pilot wanted to go on, and the flight test engineer told, no, it's a chip detector. It's a chip of the main gearbox. We need to control. So at the end, they stopped the flight. Then flight number 3, we were at 170 knots. So it was really exciting because it was already a speed which were quite significant, and we didn't encounter any big, let's say, noticed in the measurement that would allow us to think that something is going wrong. So we had some increase of vibration, but limited, no instabilities. They performed at that time some turns at 60 degrees of bank angles, so very high turns, and nothing happened. So we did continue the flight campaign, and we reached on the 13th of June 2024 the speed of 227 knots, which is over the target that we have of the 220. I think Dominique and Tony, we spoke at that time, and I told you that I was expecting some good surprises, and so we had it. I will explain later on why, but in fact, we did all this flight envelope, and if I describe a little bit more, we covered all the flight envelope except the VNE, the VD, and the simulation of engine failure. By the past, it was never the case that we did it so quickly on any of our prototypes. So we are really happy by the behavior of this aircraft, and what is really to be noticed is that when flying at 220 knots, the aircraft is behaving very well without any loads, without any vibrations, and without damaging the parts that are in the rotating frames. You remember I mentioned that all the upper deck and notably everything which is rotating has a lot of influence in terms of cost and of maintenance. This aircraft is flying fast without damaging the parts. And moreover, we looked also what happened at 180 knots, which is the VBR, the best range speed of the Racer. And at 180 knots, nothing happens. Everything is flat. So we have a very good formula in terms of a very sane formula in terms of dynamic behavior, loading of the critical parts. And we believe it is key when we want to provide solutions that will be affordable for potential customers. Design to drag. I told you drag is key for the formula. For the high speed, drag is key. And in fact, now I can give you some idea what we reached with the Racer. Analyzing the flight data, we discovered that in fact we have been able to overpass all the targets in terms of drag reduction. The Racer demonstrator is between 7 and 8 tons. And when we compare the drag of the Racer demonstrator to other aircraft that we know, we are comparable to a H125, a squirrel. So we are, it's written here, lower than a 3-ton helicopters and comparable to a squirrel. even less than a squirrel. So it's to give you a little bit the feeling of what is the effort that we have done on this aircraft. And when compared to what we did on the X-Cube, so in blue you have the current AH fleet, but if we take other fleet, it will most probably be the same curve. For the speed record of the X-Cube, we did a special effort in order to reduce the drag and reach the 255 knots. And the Racer will be able, when we would have implemented all the devices, like the full fairing, the doors of the landing gears, we will be lower than the X-Cube in terms of drag. And then, when we go to kilometric fuel consumption, I don't give the numbers here, but the blue curve is the conventional aircraft fleet at VBR. And when we compare to what we have at the moment, at 220 knots in twin engine version, we are already more than 20% lower in terms of consumption than an aircraft, a conventional aircraft from the same weight. And if we take into account the expected performance when we will have the eco mode, we will be even lower than what we have at the moment. I come back to the point of affordability. This is key here, because with a low consumption coming from the low drag, we are able to make some range. When we do some range, we are able to make some missions. When we do some missions, we can sell the aircraft. This one is too complicated. So what is it? It is the challenge of the compound helicopters. In this graph, you have on the first part of the graph on the left side, you have what represents the behavior of the pitch rod, the main rotor pitch rod, in the area of the advancing blade. And on the second part, you have the behavior of the retreating blade. Okay? So the advancing blade is submitted to the high Mach level because higher speed, and it's where we want to remain below Mach 1. If we are too close, the red line that are the flight data at 220 knots are far above. And the second one is a little bit more difficult to understand and a little bit more difficult to handle, because it's what is happening when we are in what we call the reverse flow disk. For the retreating blade, there is a moment where, in fact, the airflow is attacking the blade by the trailing edge, which creates a nose-up effect on the blade. And it happens in this circle that we call the reverse flow disk. When we have that, we have an increase of the loads. And then due to the flexibility and the behavior of the blade, you have the elastic rebounds that you see just after. And everything is about how to tune correctly this behavior. If you are able to manage both the behavior in advancing and retreating blade, you will have the possibility to fly fast without having big loads, big vibrations, and behavior that are detrimental for the formula. In blue, it is the simulations. And you can see that we have a very good simulation compared to the measurement. And if you come back to what I explained before, we have a long experience, a long history in building demonstrator, understand, exploring new concepts. We have now tools that are able to predict the behavior of the high-speed formulas. If tomorrow we want to make a serial aircraft, we are able to do it. It's written here, excellent loads prediction thanks to CFD plus flexible blade models coupling. So what is next? We are currently preparing the second flight test campaign. During this second flight test campaign, we will have more speed. Shall I give a number? We will target to reach 240 knots in cruise due to the low drag that we have. We will also, there will be also mission demonstration, eco mode function, and noise reduction. For the mission demonstration, we speak about civil and military application. For the civil, we will try to demonstrate what the aircraft is capable of in terms of range, in terms of speed, in terms of cabin use. You can imagine that we take off from a heli deck. We fly quite fast and quite far. We hoist someone and then we come back. We can imagine to make Paris to London, door to door, Issy-les-Moulineaux, London City Airport. We will see. And in military, we want to invite also pilots from the military fields to demonstrate the capability of this aircraft, not only for the speed, but also for the maneuverability, because I didn't speak about that, but in terms of maneuverability, we are comparable and even a little bit better than what we could do with a conventional helicopter. We have a main rotor. We have a main rotor, and we have the possibility to pilot this aircraft exactly as if it would be a conventional aircraft. The pilot, when entering in this aircraft, has only one additional command compared to the conventional aircraft. If you are a normal helicopter pilot, you need a half an hour briefing to be able to pilot this aircraft. There is only one button. It's the collective pitch of the lateral rotors. You push the button, you accelerate. You pull the button, you decelerate. Easy. So there is not only the speed, there is also the capacity of the aircraft to have high climbing rates, high descent rate, to maintain the attitude during a descent and to control the speed, to have a hover with angle, with some angle compared to the ground, up to 20 degrees, which is huge. So there are a lot of things that we want to demonstrate, and it will be part of the flight test campaign number 2. Eco mode. Since years we are developing with Safran helicopter engines what we call the eco mode. Eco mode is a micro hybridization of the helicopters, of the Racer formula. It is also a technological brick that we can apply to the conventional aircraft. And what will we do with the eco mode? How does it work? In fact, we start from the statement that when we are flying in cruise, we are not using the engines in the vicinity where they are the most efficient. And so we had the idea to think about the possibility to shut down or put one engine in sleep mode and fly with only one engine operative. So obviously when we do that, we need to cover the case where you have a failure of the only engine operative. And that's why with this system we need a battery that is able to provide a huge amount of energy in a very small amount of time to restart the engine that would be in sleep mode in 5 to 7 seconds. So this system, we will install it in the Racer in the year 2025, and we will fly it to make the proof that it works. And theoretically, with the low amount of drag that we have, we are able to fly up to 180 knots with only one engine. And that will give us the possibility to claim an additional 15% of fuel burn less than what we have reached currently. Noise reduction. You have seen in the video that we have the possibility to control the inclination of the rotor with this formula. Why is it the case? It is because we have an additional degree of freedom compared to conventional aircraft due to the fact that with the lateral propellers, we are able to generate a moment around the pitch axis. So at each point of any trajectory during the flight, we are able to control and to decide what will be the inclination of the rotor. And if you consider that the noise perceived on the ground by the citizen is coming from the blade vortex interaction, you can make the link between the fact that we can incline the rotor at each point of the trajectory and the reduction of the BVI. So we will implement in the autopilot low noise law that will use this capacity so that we choose any time the best inclination of the rotor in takeoff and in approach and landing phase and takeoff also phase, sorry, so that we have the first blade which is creating the vortex, and the second one which pass a little bit higher or a little bit lower than the vortex generated. And then, by that possibility, we reduce the BVI. We will use also the control of the NR. And everything mixed will allow us to reach 30% of reduction of the 70 dBA footprint. And then when I make a small status and I come back to the objectives we had from the project, the speed, we did it. The reduction of fuel, we did it. Reduction of noise, to be done. So we are not 100% of the objective achieved, but we are in a very good way. The aircraft is behaving wonderfully. I can tell you that the crew is very happy. Something I didn't mention also, but now I can do it because I still have some time. When we flew the 227 knots, the pilot put autopilot off. And then he said, 0 workload. Aircraft is fully stable at high speed without autopilot. So in conclusion, I would say that the best is to come with the Racer. We are according to our plan. We wanted to use the year 2024 to fine-tune the aircraft and reach 220 knots by the end of December. It's done. 2025 will be dedicated to mission demonstration, eco mode function, noise reduction, flight displays. And it was according to the plan. It was the plan. And so we are going in this direction with a lot of patience, with a lot of difficulties also, because it's not always easy. But for my team and I, it's a real privilege to work on such kind of innovation, or such kind of disruptive formulas. And we are very happy of the results.